Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year 1976. Stephen Hawking's paper, Breakdown of Predictability in Gravitational Collapse, presented a seismic challenge to the foundations of theoretical physics. This work, a culmination of years of research, wrestled with a profound paradox arising from the intersection of general relativity and quantum mechanics, two cornerstones of our understanding of the universe. At its heart lay the perplexing behavior of black holes, objects so dense that even light cannot escape their gravitational grasp. These celestial behemoths, predicted by Einstein's theory of general relativity, were initially conceived as purely classical entities, governed solely by the laws of gravity. However, Hawking's groundbreaking calculations revealed a startling reality: black holes are not entirely black. They emit radiation, now famously known as Hawking radiation, a process that imperils the preservation of The genesis of Hawking's work lay in the burgeoning field of black hole thermodynamics, a field that had its roots in the early 1970s. In this intellectual landscape, Jacob Bekenstein proposed that black holes possess entropy, a measure of disorder, and that their entropy is proportional to the area of their event horizon. This idea, initially met with skepticism, was further solidified by the work of James Bardeen, Brandon Carter, and Hawking himself, who formulated the four laws of black hole mechanics, mirroring the four laws of thermodynamics. The area theorem, an essential component to their work, stated that the area of a black hole's event horizon can never decrease, analogous to the second law of thermodynamics, which states that entropy never decreases in a system. This burgeoning field, however, also contained the seeds of an eventual paradox: the concept of black hole evaporation, stemming from the application of quantum field theory in the context of a curved spacetime, presented a profound dilemma. The Noether theorem, a key aspect of classical black hole theory, asserted that black holes are defined solely by their mass, electric charge, and angular momentum. All other information about the matter that formed the black hole is lost. When matter falls into a black hole, its information, including detailed properties, is expected to remain, at least in principle. However, Hawking's calculations, which suggested that black holes emit thermal radiation, seemed to imply that black holes evaporate, radiating away their mass and leaving behind a state of thermal equilibrium characterized solely by temperature. This process, if taken to its logical conclusion, creates a scenario where information about the initial state of the matter that formed the black hole is fundamentally lost, violating the principles of quantum mechanics, which dictate that information must be conserved. The precise nature of the information paradox becomes clear upon examining the implications. Consider a star collapsing to form a black hole, a process governed by the known laws of physics. This star has a definite quantum state determined by its initial conditions and composition. Through the mechanism of Hawking radiation, the black hole slowly evaporates, purportedly leaving behind only thermal radiation. The thermal radiation, however, is characterized solely by its temperature, a feature that does not account for the detailed quantum information encoded in the star. The resulting radiation is uncorrelated with the original state of the star, thus implying that the information has vanished, a violation of unitarity, the cornerstone of quantum mechanics. This violation implies a breakdown in the very fabric of predictability. Hawking's paper, therefore, didn't merely present a novel theoretical calculation, it exposed a critical incompatibility between general relativity and quantum mechanics. It forced physicists to confront the deep question of how to reconcile these two fundamental theories of nature, which operate with such different approaches. General relativity, with its smooth, deterministic description of gravity, and quantum mechanics, with its probabilistic and informational nature, seemed irreconcilable in the context of black holes. The singularities predicted by general relativity at the heart of black holes presented further complications. These are regions of infinite spacetime curvature where the laws of physics, as we understand them, break down, event horizons, the boundaries beyond which nothing, not even light, can escape, created a barrier to information, a barrier that challenged the principle of predictability. The initial framework, which provided the foundation for Hawking's analysis, involved the use of quantum field theory in the presence of strong gravitational fields. By applying this framework to the spacetime surrounding a black hole, Hawking demonstrated that quantum fluctuations near the event horizon, a region where the gravitational field is intense, would lead to the creation of particle pairs. One member of each pair would then fall into the black hole, while the other escaped as radiation. The escaping radiation, however, would exhibit a thermal spectrum, its characteristics dictated solely by the black hole's temperature and thereby lacking any information about the object which formed the black hole. As the black hole releases its energy, it emits radiation and gradually shrinks, effectively evaporating. This fundamental process underlies the heart of the information paradox. The 1976 paper, a pivotal work of Stephen Hawking, delved into the breakdown of predictability in gravitational collapse, a territory previously considered secure within the framework of general relativity. At the time, general relativity, the accepted model of gravity, described black holes as entities that, while capable of consuming matter and radiation, could only increase in size. Any information about the material constituting a black hole was believed to reside within the singularity. Hawking, however, through the application of quantum mechanics to the extreme gravitational environments of a black hole, presented revolutionary conclusions that challenged this established understanding. A crucial component of Hawking's analysis was quantum field theory in curved spacetime. This framework permitted him to examine quantum effects in the presence of intense gravitational fields, such as those near the event horizon of a black hole. The event horizon, the boundary beyond which escape is impossible, acted as a critical surface in this context. Hawking's calculations, rooted in this theoretical foundation, reveals that the intense gravitational forces near the event horizon lead to the creation of virtual particle pairs. These pairs, transient fluctuations of energy, appear and disappear according to the principles of quantum mechanics. However, located near a black hole, these pairs can be broken apart by gravitational forces. One particle falls into the black hole while the other particle escapes away from. This process, which became known as Hawking radiation, is the central claim of the paper. The escaping particle, according to Hawking's calculations, carries energy away from the black hole, causing it to gradually shrink and eventually evaporate. The radiation's nature, however, presents a fundamental paradox. Hawking proved that the distribution of the emitted radiation, the spectral properties, is purely thermal. The radiation characteristics are determined by the black hole's temperature, described as the Hawking temperature, directly related to the black hole's mass. This temperature does depend on the black hole's properties. The radiation seems to be entirely independent of the specific details of the matter that collapsed to form the black hole. This information loss, a consequence of the black hole's thermal emissions, contradicted expectations. This contradicted the principle of quantum mechanics, which stipulates that information should always be preserved. This is the core of the information paradox. Mathematically, Hawking's derivation employed the formalism of quantum field theory, including the use of the Bogoliubov transformations. These transformations permit the description of how quantum fields convert between the perspective of an observer far from the black hole and an observer near the event horizon. The Bogoliubov transformations allowed Hawking to calculate the particle creation rate near the event horizon and determine the spectrum of the emitted radiation. The key equations involved the relationship between the black hole's mass, its temperature, and the emitted energy. These equations predicted that the black hole would radiate energy at a specific rate, dependent on its temperature and mass. The immediate impact of Hawking's work was profound, triggering a wave of research and debate within the physics community. The paper provided the seed for an intense scientific dialogue. The thermal nature of Hawking radiation meant that black holes shed information. It appeared to contradict the principles of quantum mechanics. This prompted significant scrutiny. The information paradox generated vigorous investigation. Physicists grappled with the problem of how information, believed to be fundamental to the universe's evolution, could disappear within a black hole. The paper's legacy extends far beyond its initial presentation and impact. It spurred investigations. These investigations continue to this day. Across quantum gravity, string theory, and cosmology, physicists have explored potential resolutions to the information paradox, from modifications to general relativity to the possibility of subtle correlations within the Hawking radiation itself. It served as a catalyst for the development of new theoretical frameworks and mathematical tools. These tools try to reconcile the apparently incompatible theories of general relativity and quantum mechanics. The exploration of the information paradox led to developments in the study of black hole thermodynamics. These developments established a connection between gravity and thermodynamics. The exploration continues to drive theoretical physics. The work demonstrably influenced numerous subsequent investigations. It is connected to the development of the holographic principle, which suggests that the information contained within a volume of space can be described on its boundary. This principle is closely tied to string theory and the study of quantum gravity. Hawking's initial findings, particularly the thermal nature of black hole radiation, remain a primary focus. They serve as a benchmark for assessing new theories. It presents challenges for alternative models, guides the development of new, more complete descriptions of the universe's fundamental. Hawking's paper, initially met with a mixture of skepticism and excitement, has transformed into a cornerstone of contemporary theoretical physics. The work is the foundational document. The work offers a clear model, sparking deeper investigation. It highlights a fundamental conflict between general relativity and quantum mechanics. It continues to inspire researchers to search for a unified theory of everything.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.